Okay, so in this example, we're going to look at a combination circuit. And what we have is a 12-volt battery connected by one wire to a 400 ohm resistor, and then the path splits, and we have a 500 ohm resistor and a 700 ohm resistor connected. They join back together, and then a single wire brings them back to the 12-volt battery. So as I said, this is an example of a combination circuit. It's a combination of series and parallel. And I think you can figure this out by thinking about how charge would flow through a circuit such as this. So you can see that there's only one path between the battery and the 400 ohm resistor. So that's certainly a series configuration. But when it gets to the junction point here, we have a split. And charge could either go through the 500 ohm resistor or the 700 ohm resistor. It doesn't have to do both. So it splits up there and then joins back together at this other junction. So that tells me that these two, the 500 and the 700 ohm resistors, are in parallel with each other because they're connected at both ends. And then we have a single path bringing us back to the battery. So whenever you're working with a combination circuit, you want to think about how it's connected, what's in series, what's in parallel, and then kind of work from the inside out. So you want to work from the spots farthest connected from the battery to the spots connected directly to the battery. So what I'm going to do is I'm going to look at this 500 and 700 and realize that they're in parallel. And I'm going to make a box, just mentally thinking about combining these two together in parallel. I know that in parallel, 1 over the 500 ohms plus 1 over the 700 ohms is going to give me 1 over their equivalent resistance. So if we think about a common denominator here, it would be 3,500. So we have 7 over 3,500 plus 5 over 3,500 equals 1 over R equivalent. We get 12 over 3,500 equals 1 over R equivalent. And then if we flip that to get the actual equivalent resistance of these two, we get 3,500 divided by 12, which turns out to be 290. So we have 290 ohms of equivalent resistance from what's inside that box. So what we want to imagine at this point is that everything inside that box has a resistance of 290 ohms. Okay, now what we're going to do from this point is we're going to realize that the 400 ohm is connected to that imaginary box in series because it goes from the battery to the 400 to the box and then back to the battery. So to find the total resistance of the whole circuit, I'm just going to add the 400 to the 290 in a series. So I get 690 ohms of total resistance for this circuit. Once I know that, I can use Ohm's law to find the total current. So I can do I total equals the battery voltage, 12 volts, divided by the total resistance of the circuit, which is 690 ohms. And we can punch that in and get 0.017 amps. So now I have the total current and the total resistance. At this point, I'm ready to build my RIVP chart. So I'm going to set that up, R, I, V, and P. I'm going to write down the original resistances in the chart. So I have 400 ohms, I have 500 ohms, and I have 700 ohms. Now, looking at the circuit, the next step is really to figure out, is there anything I know I can put into the table right off the bat other than the resistances? And the answer is yes. I can put the 0.017 amps in for the 400 ohm resistor. And the reason I know that is because there is no way the charge could get from the battery back to the battery without traveling through the 400. If the 400 ohm resistor weren't there, they wouldn't have a complete circuit at all. So I know that every single electron that moves through this circuit passes through that 400 ohm resistor. So now I have R and I can find the voltage and get 6.8 volts. We'll hold off on power until later. Okay, so once we filled that in, what we need to do now is, when you're looking at a combination circuit, what you're going to do is either use the loop rule or the junction rule to help you figure out your next step. So in this case, I'm going to use the loop rule. So I imagine that if I traverse a loop around the circuit, I have to drop a total of 12 volts. And I know that because the battery is a 12-volt battery. So starting at the battery, if I make a loop that goes up and through the 400 ohm resistor, and then let's say I go up into the 500 ohm resistor, and then back to the battery, I have to drop a total of 12 volts. Okay, well, I already know that I dropped 6.8 volts across the 400 ohm resistor. We already figured that part out. So if the 400 and the 500 are the only two in my imaginary loop, then that means the 500 ohm resistor has to drop 12 minus 6.8. So that would be 5.2 volts. Because I know the voltage and the resistance, I can find the current, and I get 0.01 amps. Okay, now, my next step is to use the junction rule. So I'm going to say, well, I know that a total amount of current of 0.017 amps goes into this junction point here. And that means 0.017 amps has to come out. Well, we already know that 0.01 amps goes up through the 500 ohm resistor. So that means the rest of the current flowing through the 700 ohm resistor has to go this way. So that's going to be 0.007 amps. So I can put that in my table here. And then multiply I times R to get the voltage. And it turns out that it's exactly the same as the other one. You could have proven that the other way around using the loop rule. We could have gone around the loop again, except instead of going through the 400 and then through the 500, we could have gone through the 400 and then the 700, and we would have been able to figure out that that voltage would have to be 5.2 volts. Pay close attention to the fact that those two resistors end up getting the same voltage across them. Any two resistors in parallel should always get the same voltage across them, so that makes sense. And notice that the two currents add up to the total current, which also makes sense because some of it has to go through the upward path and some of it has to go through the downward path in order to get your total current. Let's find out what the power is to finish this off. So we have 6.8 volts times 0.017 amps. That gives us 0.116 watts. If we do 5.2 times 0.01, we get 0.052 watts. And 0.007 times 5.2 gives us 0.036 watts. So now we can see that the 400 ohm resistor uses up the most energy in this case. The other two use definitely less.